So let's continue our discussions in week 5 looking at multivariate statistical analysis where we compare more than two groups. And we're going to focus this part of our discussion on the Kruskal-Wallis H-test. But before we do that, we'll continue our interpretation of the ANOVA. And as we've said, our primary function in using these tests is to compare differences between groups when there are more than two groups. So we saw when we looked at the descriptive output of each region for its readmissions, there was such a spread of data. There were so many means, medians, variances, standard deviations, interquartile ranges, that the table became massive and very difficult to interpret or make sense of. And so these statistics give us efficiency in comparing between groups. As we've said, we're looking at the analysis. We've already done the description, central tendency, variance, relationships, subgroups, looking at the exploration of our data to know which analytic statistic is going to help us answer our practice-based question. And we've said that the ANOVA is the parametric test that lets us compare multiple groups. And its purpose is to look at the means of multiple groups within one test. And as we saw from our SPSS output, the means for each group, each region of the United States for the number of heart failure discharges is reported here in the mean column. So this ANOVA allows us to compare all of these means and say, are the means of these groups statistically similar or identical or statistically different? And we can do that with one test. So if you look at these means, you might say, well, there is quite a bit of variation in terms of the means and the standard deviations around those means, and difference in the sample sizes and the numbers. So if you look at the output in your descriptive table, you'll probably say, well, looking at it, it looks like the means are different. So when you run the ANOVA, now we can statistically say, are these means different or not? So the place I'd like you to focus on in this table is really the final column, the significance column. This is the p-value for ANOVA. And this is the key number that's going to aid your interpretation of the test. We'll always go back to our null hypothesis. So for ANOVA, the null hypothesis is that the means between the groups are identical. So if our p-value is less than 0.05, we can reject that null hypothesis. And so we have here a significance level, or a p-value of 0.000, meaning that we can very clearly reject this null hypothesis that the means between each region of the United States are the same. And so our visual inspection here of the means in this column is supported by this formal statistical test. Now, what do you do if you get a significant ANOVA test? It indicates there are differences between the groups, but the only way to formally know which groups are different is to statistically test them one by one. But instead, what you would need to do is you'd need to run a t-test between each pair of regions. Now we have 11 regions here, and you'd have to run a t-test between every single region to identify where that difference lies, if you want to do it formally and statistically. But what we need to do is come back to our problem statement, our primary question, and let that question drive which regions we would test, because it's possible that our question is really only about one state within New England or one state within the Southeast, and that question will help us figure out which t-tests, which regions we want to compare. So let's suppose for a moment our state of interest is in the South. We're going to say Georgia. And so we want to see if states in the South are different than states in New England in terms of the number of heart failure discharges. So let's test that formally. So we'll go to Analyze, Compare Means, and these are independent sample t-tests, so we're comparing the means of two regions that are independent of each other, and we're going to compare them based on our heart failure variable. So we'll scroll through and find our heart failure heart failure discharge number. So we'll scroll through. Here we are, heart failure discharge number. So we'll put that in our test variable column. And in our grouping variable column, instead of the state number, we're going to remove that, and let's go for region. Region. Now we need to know which region is New England and which region is the South. So if we didn't already know that, we could go back to our codebook and run it. So we have either run codebook to see how the regions are coded numerically, or remember that New England is 1, so we make that group 1, and the South is group 6. So we're using the specified values for these two regions, and we're going to compare the number of heart failure discharges in those regions using a t-test. And this t-test is a follow-up to the one-way ANOVA. So the one-way ANOVA showed that there are differences among these 11 groups, and now we're going to test if there's a difference between the South and New England. When you go to options, the default options should work fine for you on this test. So it will say, all right, let's generate this test statistic. So the group statistic output is going to be your key summary table. You can see here the mean for the number of heart failure discharges in New England is 535, and for the South is 314. The number is fairly similar in the mid-300s, and the standard deviation are somewhat different. So the means are different and the standard deviations are different, although the number are close. So we know that this would violate the assumption of the t-test for equal variance because the standard deviations are so different. So we would need to use the t-test for unequal variance, or where equal variance is not assumed. So we'll follow that in our output table. Don't worry about the first two columns. We're not focusing on those in this course. And the next two, we're also not really focusing on here. That's if you calculate it by hand. But SPSS has done the work for us. So we'll look here at the significance, the two-tailed test of significance, or the p-value of the equality of the means for New England versus the South. So our null hypothesis for the t-test, remember, is that these means are equivalent. So with a p-value of less than 0.05, we can reject that null hypothesis and state that statistically there's a difference between the number of heart failure readmissions for New England versus the South. So that's how we would move from a one-way ANOVA that demonstrates differences among the groups to a specific two-group comparison using the t-test. That's for data that are normally distributed. We've executed the test of individual pairs because our p-value for the one-way ANOVA was less than 0.05, suggesting a difference among all groups. We've tested a specific set of groups with a t-test. Now that's a parametric analysis. Let's take a look at the Kruskal-Wallis test that does a non-parametric analysis when these data are not normally distributed. We're going to again use the 11 regions, and we're going to look at the Kruskal-Wallis test. And the Kruskal-Wallis H test also goes by the name rank ANOVA, so that instead of ANOVA, which is testing the difference in the group means, the Kruskal-Wallis test is testing difference in rank. So it's testing differences in how these groups are distributed. And it also goes by the nickname the group Wilcoxon rank sum test. So it's again testing differences in the rank sums, but instead of just in two groups, like with Wilcoxon, it's testing in more than two groups. So Again, its purpose is to test difference in groups that are not normally distributed, and it's the sister test to the one-way ANOVA. The null hypothesis is that the samples in each group are from identical populations. So it's not exactly the same null hypothesis as the ANOVA, but it's analogous. Practically, the null hypothesis is testing if the groups are not different. And so it says that the predictor groups are not different on the particular outcome. So if your p-value is less than 0.05, it suggests that the groups are different. Greater than 0.05, it suggests that the groups are not different. And as with every test, it has assumptions. So the Kruskal-Wallis test, the non-parametric sister test to ANOVA, assumes that the outcome measure is on an interval or ratio scale, and the predictor is on a nominal or interval scale. So it's using categories and comparing categories on an interval or ratio outcome measure. It also assumes that the observations in these categories are independent of each other. It says that the predictor variable distribution and variance is very similar, and that if that's the case, you can compare the medians directly. If the distribution and variance of each of the groups is not equivalent, then you're comparing the rank of the medians. And we'll talk about what that means when we look at our data set in SPSS. So we come back to SPSS and we go to Analyze. We select non-parametric tests. These are independent samples. They're not pre and post, which will be related. And it's not one sample where we're comparing one region to a specified value. We're comparing one region to another. So these are independent samples. And we're going to choose Customize Analysis under the objective. Then we'll select Fields. And we're looking at the number of pneumonia readmissions. And now for our groups, we're going to choose the regions. So we're going to compare if the number of pneumonia readmissions is similar or not between these regions. And we're going to select the Mann-Whitney U-test. Now this is the same essentially as the Wilcoxon rank sum test. It goes by both names. SPSS likes to call it this. So let's run the analysis. Now, what we have here is that it's unable to complete the test. So why is that? That's because we've selected a two-group comparison, the Wilcoxon rank sum or the Mann-Whitney U-test. But what we want to do now is, instead of comparing the two groups like we did before, we actually want to compare all groups. So let's do all groups. That's the independent sample test under non-parametric. And instead of the Mann-Whitney U, we're going to do the Kruskal-Wallis test. So you can see here, we call that the one-way ANOVA of K samples, or an unknown number of samples. So now the Kruskal-Wallis will let us test the difference in multiple samples within one test. Now this time, this is exciting. Look what we have here. Our output gives us the null hypothesis, the test, the p-value, and the decision all in the output. So it makes our job a lot easier. It says we're testing the null hypothesis that the number of pneumonia readmissions is the same in each region of the United States, with a p-value of 0.000, so much less than 0.05. So we reject the null hypothesis and we conclude that the number of pneumonia readmissions is statistically different by region. So what you would now do is you would go and compare individual regions that are relevant for your problem. You go back to non-parametric test, independent samples, and this time you would use the Mann-Whitney U-test to compare one state to another. You go back and modify your groups, and instead of doing all regions, you would need to create a variable for those two states using the skills that we talked about before. Once you create those two states, you can run this analysis as you have done previously.